Do you guys have these first three graphs already? I don't think I haven't started, but it will. So, up to it. Let's recall what these transformations do. This minus 2 inside of this parabola does what to the parabola? Right 2, good. I'm going to color that to see. Shifts it right 2. And then what does the negative do? It flips it goes down. Yes, thank you. It makes it go down. So what's the pattern for an x squared? Over 1. Over 1 up how many? 1. And then over 2 up how many? 4. But if the negative is there, I'm going to go down, right? So very quick review. That should be about right. My bouncing is off so much that it's making my calibration off, so graphing when it's not on the right spot is tricky. Okay, what about the next one? The shape is an x cubed. What does the minus 4 do? Good. So down 4, and then what's the basic pattern for an x cubed? Over 1 up 1, over 2 up 8. And then you need to know that this one is like this, like the drain pipe, right? Where it goes like this. So over 1 up 1, over 2 up 8, really skinny. Something like that. Is that okay? Yeah. And then what about this square root? What does the 2 do? It's stretching it. It's going to pull it taller, right? So the normal pattern, because this is the inverse of the quadratic, we do up before overs. Up 1 over 1. Up 2 over 4. That's the general pattern for a square root. How does the 2 affect my pattern? I'm going to multiply all of my ups by 2. So from my starting point, I go up 2 over 1. And up how many? 4 over 4. And then what would be the next one? Up 3 over 9. But we have to double that, so up 6 over 9 gets me just off the grid, I think. So something like that. Yes, a lot of people doubled the overs instead of the ups, and so they made their graph look something like that on the test, in which case you got partial credit. Okay, so really quick, how does multiplying the parent function by a -1, like this right here, affect the graph? It flips it, good. How does multiplying the parent function by a 6 affect the graph, like this one? Good. What about a 1/2? Good. Is it necessary to use the parent function when graphing? You have to use, like, to explain. Did we graph the parent function? Some teachers make you graph the parent function before you graph the transformation. Is that necessary? No. Not always. Some teachers like it. I am not one. I don't really care. But what do you need to know about the parent function? Ish fixes everything. It's a really good answer. However, if somebody is asking to marry you, you don't say ish. That needs to be a yes or a no question. Will you marry me? Ish. That's not going to go over very well. No, that is a yes answer. It's yes, please.
I know. Yes.
Okay, moving on. What's that? Yeah. I have a rough week. Yes, my car started. Thank you. Okay, so something to take note. This function, while you're talking to each other, those are all technically different parent functions. I'm just kidding. I love it. I love being raised. He doesn't watch this, so fine. I feel bad. I was home the other day and I'm like, I love being a mom. Do I really reflect that? Because the other day I was like, anyway, we were talking and I said, what do you want to do after high school? And somebody was like, I want to study abroad. And I said, you should, because I don't have very many regrets in my life. And it's not like a regret. I got married very young, and it was a long time before I started having kids. I wish that I would have traveled more. I wish that I would have taken advantage of different opportunities. Because once you have kids, somebody was like, your life's over. And I'm like, exactly, your life's over. Which is not actually true. However, it is much harder to go to Germany with a 1-year-old and a 4-year-old and a 7-year-old. So, and then I was like, crap. And then I thought, do I even have any pictures of them in my classroom? No. I do like being a mother. I do like being a wife. I do like being a teacher too. So anyway, so if I ever express my distakes towards my family, it's not actually true. Yes. Anyway, back to this. These are all different parent functions. If we looked at this right here, y equals a times b to the x, you had a couple graphing problems on your assignment last night. Do you remember which piece did what? What the a did and what the b did? The b was the multiplier, right? It was the y-intercept. Good. So the a is the stretch, really. It's the same a as before. It's the stretch. It happens to be the y-intercept in this case, but it's the stretch, because normally the parent function goes through 1. So if a is 5 and it stretches up to 5, it's a stretch. Put your phone away, please. Please. Thank you. So the multiplier here is 2, the multiplier here is 3, the multiplier here is 4. Okay, moving on. The factor a and y equals a times b to the x can stretch or compress and possibly reflect. So, you with me? Put your phone away, please. Okay. So just like a before, a can stretch it, a can compress it. I can't write in white, and my background is white. Start again. And it is possible that a will reflect it as well. The graphs 2 to the x and y equals 3 times 2 to the x are shown. So the red graph, sorry, I hate shushing people and then I realize you're talking after this. So shushing them is fine though. The red graph is 2 to the x. The blue graph is 3 times 2 to the x. What's the difference between them? The blue one's been stretched taller, right? Because the a is 2. Or 3. Now, this was designed how I taught it last year, so we might do it a little bit different. You're welcome.
To make it easier on us for it?
Yes.
Hallelujah.
So we actually, I have a tape table. I'm not going to use the table at all, if that's okay with you. If I can show you the pattern again on how to do this. Now, if there's any shifting, we might see some shifting going on over here. In this case, we don't. Then we have to do something extra. But out of this, the 1/3 and the 3, which one is my starting spot? Hold on, give me 1 second. Come on. I don't want to do that one first. Can you flip the page? Can you look at example 4? Yeah, no, yeah, 3. Let's look at example 3 first. Let's look at example 3 first. How does the graph of y equals negative 0.53 to the x affects the parent graph? Well, the parent graph is 3 to the x. This is the parent. How does the 0.5 affect that graph? It's going to be compressed. How does the negative affect it? It is going to be reflected. So I know that I told you that the 3 was the multiplier. If a is ever negative, that needs to go with the 3. So to get my next point, I would multiply by a negative 3. Well, sort of. Is that true? I don't know. Let's see how this goes. Part B first. Where's my y-intercept on part B? Okay, so I'm starting up here. It's a really bad scale. Let's change the scale. 6, can we change it by 6s? 6, 12, 18, 24, 24, 2, 3, 4, 5, 6. So that would be 36. Anytime I change the scale, there's that one. So we changed the scale. I didn't put the 6s along the way. I just put that as a 36. So my first point is going to be what? 24. So 1, 2, 3, 4 right here. And then to get to my next one, what do I do? I half it. Good. So now when I go over 1, it's going to be here. And then to get my next point, so I'm at 12, and then 6, and then 3, and then at that point, you just kind of try to get it closer and closer to 0. If I'm halving it as time goes on, what am I doing on the left? Doubling it. So the next one over, if I'm at 24 here, it needs to be clear up at 48, right? Which is off the grid. However, I want to point out where it is, simply because I need to know that that graph is not going to cross the next line over. Does that make sense? Okay. Good. So, come down. Does it ever cross the x-axis? No, because if I keep dividing by 2, will I ever get to 0? No, you can still divide by 2. Phones, please. This is the third time, by the way, I've asked somebody to put the phone away. All right, let's do the next one. Hey.
Can I just go back to school and
You want to just drop it off? What? Okay, and I'm using you as a tutor, right?
Yeah.
Perfect. Which class 3? Did you look at my schedule already? You know what class that is? I don't know.
I don't know. All I know is that you told me
Either?
to go to part 3 first and last.
Got it. Perfect. You're welcome, thank you. I don't know my schedule next year. I know that I have. I know that I have like secondary 3 and then 2, and then secondary 3 and then secondary 3 light, secondary 3 light. We're offering a new class next year that I'm starting, which makes me nervous. Okay, the parent function on this one is what? 5 to the x. But this time the negative has what? Flipped it. So when I'm doubling it, I'm going to double it in the negative direction. Where's my y-intercept on this one? What does a equal? So technically b equals 5. A equals -1. Good. So my starting spot right here is -1, which my grid is kind of messed up again. That's okay. -1 goes about right here. So get to my next point, I have to multiply that by what? By 5. So 1 times 5 is right here in the negative direction. Multiply that by 5, we get what? 25, which is right here. So technically, this is an exponential growth. It's just exponentially growing in which direction? Down, right? On the left, divide, pretty much 0. Something like that. So as long as you know what the parent graph is, what the multiplier is, and what the starting spot is, and if it's going up or going down, these are pretty easy to graph. Is that okay? Do another one? Go back to the page before. Let's find that one that we skipped. What's the function? Okay, so what's my a value? So -1/3, this right here. Oh, 3. Oh, I see what you're saying. Yes, done? Oh. There we go. Oh, same time. I thought that was just done. I knew it. Oh, wait, give me that. Okay. Okay, so my starting point is -1/3. No.
I did.
100% like I like to do this last group. Go ahead. Yes. Yes. That number. You multiply that one. Yes. 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 So this is the first time, really, I guess we saw an absolute value a little bit. This is the first time that we're going point by point by point by point and not going back to the starting spot. Okay, so right here we're at negative 1/3. I multiply that by 3, so this still is my multiplier. Multiply that by 3, we get what? 1. Multiply that by 3. What's my scale here? Still 1. So multiply the 1 by 3, we get, is that okay? Okay? Yeah, negative 1. Yeah, sorry. So it's something like that. This grade is not a good grade for that. All right. How are we looking at? Any questions on graphing? Are there any more graphing examples? Okay, so I'm going to pause this really quick. Flip over to your homework. Okay, let's move on. No, I think, no. All right, so now let's talk about another transformation. Oh, come back. Please. Hold on, finish that sentence and then be done. I can tell that you're paying attention because I can see your eyeballs. Yeah, there's two different things that could happen with some transformations. Based on what we learned last unit, which one of these, the first or the second, would you guess is the left-right movement, and which one would you guess is the up-down movement? So left-right, raise your hand if you have a guess, don't shout it out. Which one do you think is the left-right movement? Lindsay? The top one. And that +4, do you think that moves at left 4 or right 4? That's left 4, good. Hey guys, don't work on your homework. So that one is left 4. This one is up or down? Up. It's the same rules as all of the other ones, which is why we took the time at the very beginning to look at those other ones. So flipping back to your notes, I think that I may have missed something right. Nope, I didn't. So let's talk about how these would transform the graph. This one right here moves the graph where? Right forward. On part C, this moves the function where? Left 2. Part B, a lot more is going on here. The function, what does the 10 do? Up 10. What does the 20 do? It is a stretch. Good. It's also the y-intercept, right? And then what about part D? What does the 0.5 do? Sorry, what does the +5 do? Up 5? What does the 5 in front do? It's a stretch. Even though this is a 0.25, is it still a stretch? Yes, it's just a decay. And back this up just a little bit so I can see what's going on. Now graphing these ones is a little bit different than graphing the other ones. I'm going to do this in 2 parts. I'm going to start with this part and ignore the -1 and the +4. You could do it all in one step. However, I feel like you're more likely to make a mistake. So if I start here, where is the y-intercept? Do it in orange. Y-intercept here would be what? The 3 or the 2? The 3. So my y-intercept is 3. That's not what I wanted. Hold on. I'm going to write it, when I did this, on my answer key, I did this part in pencil, and then I did my final answer in pen, bless you. So if you wanted to highlight your final answer, you could. I don't know, it doesn't really matter, I guess. I don't know, whatever you want to do. So my starting spot is 3, and then to get to my next one, what would I do? The multiplier is 2. So to get to my next one, 3 times 2 is 6, and then to get to my next, oh, hold on, my scale's off. Can you read what the scale is? Because I can't. Everything's 2? Okay, so just kidding. My starting spot's here then. And the multiplier is 2. So now we're at 6. And then what? 12. And then what? Oh, sorry, so just bad. So just 24, right? Ish. Okay. Now if I'm doubling as I go to the right, what am I doing as I go to the left? Halving. So if I'm at 1 or at 3, now I'm at 1.5, which is that right here. And then at that point you can just kind of hold on though. Now I want to look at the transformation. So this actually is not my graph. That's just the first part of my graph. The graph has been moved, right? From here, what has happened? Right 1. And from here, up 4. So I'm going to take each of these points and go right 1 and up 4. Right 1, up 4. Right 1, it's harder. 1, 2, 3, 4. Right 1, up 4. Alright. Right 1. And the asymptote, if you were to put it in, your graph would not be able to cross this line. So I want you to put the asymptote, the horizontal one, on there, so that as you're drawing your graph, it's going to get closer and closer to that line. And it will look like that. So, if I were to recap, what I do here is I start by just drawing the y-intercepts and the multipliers. Then I'm going to take each of those points, rather than doing it on the table. I could show you how to do it on the table if you want to. But rather than doing it on the table, I'm just going to move them up and down. It was harder on this one because the scale was off by 2s. I believe, on your homework, the scale is 1. It makes it a lot easier, better accurate. Okay, so let's do another one. The first thing I look at is this. What is my starting spot? -2. Ooh, my scale is by 5. Who wrote this? Yeah, it was me. Okay, this is a big, that's what I want. That's okay, we can figure it out. I start at -2, and to get my next point, what do? I take the -2 and I multiply it by 3. So if I'm at -2, multiply that by 3, I'm at -6. -6 times 3 is -18, which is, I used by 5. Alright, and if I'm multiplying by 3 going to the left, what do? Divide by 3, we actually know. Divide by 3, and this point seems bigger. Okay. Now any questions with that so far? Just the initial point before the shifting. Are you okay with that? How do I shift it then? What does this +1 minus 5 do? Each point needs to go left 1 and down 5. So I take this point right here, I go left 1 and down 5. I take this one, go left 1, down 5. Now conveniently, 5 is like the first box, right? Left 1, down 5. So it'll be in the same placement as it was before, the first box down. And your asymptote on this one is going to be right here, right? Because originally the asymptote was at 0, but it's been shifted down 5, so your asymptote this time won't ever cross this. And then closer to this line. Maybe we have more on the next page. Any initial questions before we move on? This shifting, the up-down shifting, that's where it's going to be. Brayden, did you do this in Christensen's class before? Did you do it on tables? Like, do you remember this at all? Okay. Okay. All right, let's move on, see if there's anything on the next page. If not, oh, there's not. Oh, we need to come back to that. Hold on. I think we're going to skip that completely. We're skipping example 7. If you'll look at your homework, that wasn't very many examples.
Your homework, skip number 7, okay.
No, I didn't. On the notes, we're skipping example 7, not on the homework. And I'm almost positive there's no homework problems like it, so I think we're okay. Shh. Are you okay with the first page? Any questions with page 1? Problems 1, 2, 3, or 4? Okay, let's do. Just, okay, which one? Number 2. Okay, number 2. Where is my y-intercept? At -1/2. This is an exponential growth because that's a 2. But which direction am I growing in this case? Because that is negative, I will be growing in the negative direction. So it's going to infinity, it's just going to negative infinity. So that -1/2, if I multiply it by 2, where am I at? -1. And if I multiply -1 by 2, I'm at -2. If I multiply that by 2, if I multiply that by 4 or 2, and if I multiply that by 2, now I'm at 16. And when I grade your test, I'm looking for point. And if it's wobbly in between points, I cut you some slack, but I look to see if the points are in the right place. So when you grade your homework, you should do the same. Now on the left, I don't really care. I just know that they have to be almost 0. Something like that. Is that okay? That's what it would look like. So looking at the next page then, let's just do one of those together, and then I'll give you the rest of the time to do the other 3. Let's look at number 6, since we're right here. Where's the y-intercept in number 6? Y-intercept is what? Number 6? 5. Well, now technically this is before the shifting, right?
Yeah.
And then my multiplier is what? 2. So to get my next point, I'm at 5. Now what? 10. Now what?
Don't you think by 1 though?
We will in a minute. Now what? Now we're at 20. Good. And going on to the left, if I'm at 5, then over to the left would be 2.5 because we're dividing now. 1 and whatever quarter, and let's leave it at that. This is pre-shifting, right? So to get around using the table, I'm just putting my dots on there before I start shifting it. However, this one has been shifted. The -2 means it's gone where? Right 2, and the +1, up 1. So each of these points needs to go right 2, up 1, sorry, right 2, up 1, right 2, up 1. It's easier when they're actually on a grid mark. Right 2, up 1. Where would the horizontal asymptote be here? This is the horizontal asymptote. I like to draw it simply. Oh, I like that though. I like to draw it simply so that as I'm drawing my other points, so half it, it's a lot easier to tell where they are, and so I don't cross that in.
So do you need to graph the square function?
Nope, I just want the blue. However, if the orange substitutes the blue, then do it. If not, just don't make a mistake. Yes. The horizontal asymptote is always this number right here. So in this one, the horizontal asymptote will be 1. This one will be -1. This one will be -2. Okay. Any other questions? We have a few more things we need to do, but not before lunch. So I'm going to pause this again. Don't forget to remind me to start it. So you have to look at this kind of in 2 parts. Are you okay with the first page where this is your starting spot and that's your multiplier? Okay. So we're going to start there with these ones where this is my y-intercept, this is my multiplier. We're going to ignore this +1 and this +1 temporarily. Okay. So my starting spot is 4. And then to get to my next point, I half it, right? So 4, 2, 1, 1/2. I'll stop there. And then on the left, I was at 4, so 8, good. 16, good. And then there's that. Now, so the same transformations happen as happen with our parabolas and cubes and square roots. So if it's with the x, then, and there's a +4, that means I'm going to be going left 4. And if it's outside of the x, just off to the end, it means I'm going up 4. Is that okay? Well, I've already talked to you about it. So going back to our homework, that means this, all of these dots need to move. This is up with the x, right? So that's left 1, and this one's on the outside, so it needs to go up 1. Is that okay? So then I'm going to take each of these points that I already have, move them left 1, up 1, and this is my actual function, left 1, up 1. So doing it this way makes it so I don't have to worry about the table, like plugging it into the table. Last year, we had these tables, and they were like 4 different bars, and the things were adding and subtracting, and it was so confusing. But I didn't know any other way to teach it. Then I taught in secondary 2, and it was confusing. Interesting, okay enough. And now we do it. Now, one thing I'd like to point out is that this number right here is the horizontal asymptote. I like to draw that in because it helps prevent, like as you're putting your points down, it helps prevent you from crossing that line. The shift up. It's always just the last number. Because normally on the parent function, the horizontal asymptote is 0, but if my graph is shifted up 1, so has the horizontal asymptote. So for this particular problem, it looks like this. Thank you. Yes. So if the 1.25 is my growth rate for the entire decade, do you suppose my yearly growth rate would be higher than that or lower than that? Lower. Is that okay? Okay. In fact, if I were to come up with an equation, and I always have to think about this 7 times in order to get it right. If I were to come up with an equation, let me think, hold on. I always write it down, then I have to try it. If I have 1 decade, does that equal 10 years? So if I plug in the 1 for the decade, would I get 10 years? And if I plug in 2 for decade, would I get 20 years? So does this equation make sense to convert from decade to years? It's only the lunch bell that does that too. I don't know what. Now, if let's read this equation or the sentence. Models the population of a city in thousands after D decades. What exponential function models the population of a city after T years? So I have to make a substitution to go from decades to years, which means I need to take this D and replace it with something. What do I replace it with? Solve this for D. What is it? So if I want to know how many decades there are, I take how many years I'm at and I divide it by 10, and that would tell me how many decades, right?
Or you can just divide it by 10.
Hold on, is that okay?
Yes.
Is that okay? So if I'm replacing this population in terms of years,
You can just do 1/10 of the original.
instead of D, I'm going to say, I can say T over 10, or I can say, I don't know, hold on. Is it okay if I say 1/10 times T? Is that okay? Is that the same thing as T over 10? Are you with me? Yeah. Okay. Now, if I want to find the annual growth rate as opposed to the decade growth rate, I would just have to figure out what that number is. So will you take 1.25 and raise it to the 1/10th power? So the first question says, what exponential function models the population of the city after 2 years? This is it. P equals 80 times, what's the new growth rate? 1.022 to the T. That means my annual growth rate would be what? Remember the equation that we did yesterday that was A of t equals p times 1 plus r to the t, like that? And this is the growth rate. So if I have 1.022, what would my growth rate be? Would it be 1.022 or the 2.2%? Questions on that? What is the annual growth rate of the student population? Any questions with that? So we take it, we substitute it in because my time over 10 is the same as decades. We have a new growth rate. The function is in terms of decades, not years, yada, yada, yada. We just did that. Does it ask us anything about evaluating? No? Is this a growth or is it a decay? It's a growth rate. We're going to call it a growth rate because this is bigger than 1. If that was 0.98, we would call it a what? A decay rate. That's fine. Okay, part B. The function B equals, fluid model, the value of an antique car in thousands of dollars, D decades after it's sold. At auction for $110,000. So this 110 is this 110. Is that okay? What exponential function models the value of the antique car after t years? So how do I do that? I take v. Now what? I'm going to raise it to the what power and why? Put your phones away, please. I raise it to the what power? Okay? Because if I were to multiply, it takes 10 years to get 1 decade. If I had 10 right here, 10 times 1 times would be 1 decade. So that's my conversion for the right here. Yes, Jessica. Yeah, I dropped the 1 because in the equation, the 1's not the growth rate, the rate is everything besides 1. Somebody please tell me what 1.16 to the 1/10 is. Do you have it? 1.01, give me one more. 4. So my vehicle, that's the equation for the annual rate. So this is the first question. What equation models the annual rate? What is the annual growth rate of the antique car? So the growth rate comes from here, 0.014, so it's a 1.4% growth. If the question asks me the worth of the car after 7 years, do we expect this antique car to be growing in value or depreciating? Well, based on the equation, we expect it to be growing, right? So how would I figure out the worth of the car after 7 years? You would plug in a 7. So 110 times 1.014 to this 7, and you would get a number. What's the new one? Okay, I believe there are 2 of these on your homework, so I'm pausing really quick and letting you work on those. E is a number. You can probably find it on your proxy. E is an exponential number. Yeah. Okay, so are you okay with 1 decade equals 10 years? So it seems like D should be 10 times T, right? However, if I plug in 1 year, does that equal 10 decades? So it's kind of backwards, right? So I'm okay with this conversion, but If I were to talk about 12 years, and I want to know how many decades 12 years were, decades are 1/10 the size of a year. So it's going to take 10 years to get one decade. So if my time is 10 years, and I want to know how many decades that was, I would plug the 10 in here and I get one decade. Okay? Because it's going to take 10 times the amount of years in order to get the one decade. A decade is 1/10. The amount of decades equals 1/10 the amount of years. Last year, I remember this problem, and I'm like, I had it this way, and we did the problem wrong, and I sat there, and I'm like, I don't know what's going on. And it was my first year ever teaching secondary 3, and there was this really smart kid, and every time I got, like, mind boggled like that, I'd look at him, like, with this, like, and he's like, I'm a student. I know, I'm a teacher, I don't know what I'm doing. So, yeah, I feel good about that. It's just really hard to explain.
When you want to write the equation, well, I can take tiny steps.
Go for it. Any questions with those 1 and 2? Okay. Yes. And then get that. This is 2 to 1 then. All right. Hopefully at least you've had a chance to look at the 1 problems.
It's pi, are you serious?
It's not pi.
Yeah, it says it right down the notes.
Am I still recording? No, not. Good. Resume recording.
What is the symbol? Right there.
All right, let's move on.
So wait, what did you want for the growth rate?
Let's move on now. Now we're going to talk about the natural number. Well, maybe I was recording the whole time. I don't know. Gentlemen, now we're going to talk, well, I'm starting.
Okay, good.
Now we're going to talk about the natural number. So, just like pi is a number, it's ugly, it's irrational, it goes forever, 3.14 represents something. Is this a variable? Does it represent, a variable means a symbol that could represent various amounts of things. So does pi ever represent anything other than 3.141? No, so technically that's not a variable, pi is a number. So there are other symbols in math that represent numbers. One of them is E. E, do you find that on your calculator?
No.
It's on there. It should be this, you see the ln button? So on the far left side there's x squared, the log, the ln. ln stands for natural log, which we will be doing later. Natural log and the natural number are the inverse of each other. So if you go second ln, you should get the e, right? And if I want to know what e equals, do e to the first power, what do we get? 2.7 again. 1.8, and it goes on kind of ugly, right? So natural base exponents are using the base e. Anytime you have an account or something that is compounded continuously, you'll be using this natural number. How it's derived, I'm not entirely sure.
What's the
But if anything, so like bacteria growth, where you're just like compounding it over and over and over and over and over again, would be using E button. So the first thing I want you to do, notice when you did that second ln and you got that E, it came right up with the power, because the natural number E is used with exponents. So the calculator just knew that he would be doing in this route. So what's E squared? And what's E to the 6th?
Well, let me do E to E.
Do E to the 1.
Oh, okay.
And in order to do E to the E, you'll have to do E to the 1. 15 point what? Okay. Now there's another equation that we will be using with regards to growth. And the key word here is continuously. So the formula for continuously compounded interest uses the number E. So just like last time, A is the amount in the account after T time. P stands for principal. Interest is R, and T is the time in years. These two formulas you need to have memorized, and you need to know when to use them. So again, what's the key word for the first formula? It's continuously compounded. Yep. If it was an annual compound, or if it's just increasing at a certain rate, we'll use the other formula. This one? Are you talking about the dear question stuff? Okay, I'm not on that one. So give me a second and I'll get there. And let's run a different problem. But we haven't done any examples, Brandon, and I need you to not jump ahead unless you want to just figure it out on your own. Alright, so example 10. Do we really have 10? I don't know. Suppose you want a contest at the start of the 5th grade that deposits $3,000 in an account that pays 5% annual interest compounded continuously. So there's that key word. A, how much will you have in the account when you enter high school 4 years later? So the formula is the amount after 4 years. How much was the initial deposit? 3,000 times E to the, now it brings it up in the exponent. If you have one of the smarter calculators that stays up in exponent, you can just plug this all in. If you have an older model, you may want to put parentheses here. What's the rate? 5%, so how do I put that here? 0.05. Times time, how long is it? 4 years later. So let's plug that into the calculator, especially if you have a slightly older model. Let's make sure everybody gets the same answer. You can't do 1.5 or you'll get it wrong, because there's no 1 plus on there. So, do you have that, anyone? Point. 2.8? 2.1? So we're always round to the penny when we're dealing with numbers. We always round down when we're dealing with animals, because you can't have 7.3 animals.
Let's say I'm missing a leg.
Yeah, well, nope. He's not missing a leg. 7 cats or whatever. All right, let's do the next one. How much would you have in your account when you graduated from high school? So when was this in? At the start of the 5th grade. So 5th to 6th, right? 7, 8, 9, 10, 11, 12. How many years is that? 7. Are you okay with that?
Oh, dear.
By the way, did everybody get this 3664? Times E to the 0.05 times 7. What did we get here? $42,000.
Oh yeah, 4,257. Sorry.
Point.
Point 20.
Oh. Fantastic. Now, next question. Using both of these examples, what happens if my interest is 7 instead of 5? So let's do both of these and see what a different interest rate does. So the first one, 3,000 times e to the 0.07 times 4. Will this half the class do that? And then the other this way half, 3,000 times e, wait, in front of me, 0.07 times 7, whatever, I'm just doing this. What do we get here? Do what in the front of your sentence? In a way?
Yeah.
Okay, what's this first one? You guys have it?
No.
Yeah,
Oh.
3,969.39. So having 2% more interest, so I use $300 more. What about this one? 0.295. So 4896.95. You can't tell as well as scribbles? No. 4,896. So on that one, having a 2% higher interest rate earns $650 more. So clearly the higher interest rate is better, right? Okay, moving on. Example 11. Find the amount in a continuously compounded account for the given conditions. The principal. Oh wait. Are you okay with those? Do we have to keep doing them? You can plug them in and you're good? Okay, let's move on. Yes. Yes. Oh, that is on paper. So the two equations you need to know and when to use them. If it's just a simple interest, that's kind of the key word here. You'll use this formula. Now it has y there instead of a of t. Is that okay? Yes? No? The other one, compound continuously uses the first. Those are the two differences. And I believe that is the end of the notes. That's it. Thanks for watching. Peace out.
Being here, people.